Okay. Yeah. So, yeah. So let me just do a quick recap of what we did last time. So I think towards the end of the class, I was kind of rushing through. So at the outset, I want to tell you, like, there were some algorithms, like there were some people who I think they got a bit panicked because they didn't know about some of the maths flow and cut algorithms that I just briefly mentioned last time. So I don't expect you to know this at this point. Okay. Uh, all you need to know for this course is linear algebra and calculus. Okay, so you need to brush up those, but everything else that is required will be covered in the class. Okay, so since there are people here from third year BTechs, fourth years, and MTech and PhDs too, so the class is set at the level of the third year BTechs. Okay, so don't worry if you haven't come across these topics before. It's absolutely fine. Okay, so yeah, so let me just do a quick recap of these problems because I went a bit fast last time. So last time what I did was I was trying to give you a flavor of these optimization problems. Okay, so one example we took was you want to send some oil from S to T, and there is a capacity constraint on each of the links. Okay, and you wanted to find a configuration where you can send the maximum possible amount of goods or amount of oil through this network. So one of the answers here was, yeah, I think, the answer was reported as 11, but the flow was not constructed. Okay, so that answer is not complete because, the upper bound was constructed, but it's not clear that that was a tight upper bound. Okay, so let me just explain what I mean by this. So with this network, the ideal thing that you want to do is, okay, you first make an attempt. Okay, so you want to exactly find how much you can send through the network. So the capacity constraints are met, and at every node there is no balance. So what I mean is the inflow is the same as the outflow. Whatever is coming into the network exactly leaves, and nothing is remaining at the node. Okay, so one possible solution here, I don't say this is the optimal, but one possible solution is this configuration here. So this was just by inspecting the network, you could come across this. Okay, so
Ma'am,
basically yes.
ma'am, you haven't yet shared your screen, I guess.
Oh, okay, I'm sorry. Okay, I'm so sorry about that. Okay, yeah. So the screen visible now?
Yes, ma'am.
Yes, ma'am.
Okay, well, thanks for pointing out. Uh, so I guess even the announcement that time you didn't see the screen. So just to mention it again, the resources have been posted on the web page. Okay, so you can just take a look. Okay, yeah, the first one has already been posted. Okay, so now, yeah. So what I was trying to say here is, yeah, this was a problem that you looked at, right? You want to send some flow from S to T. Okay, and you wanted to send maximum flow so that at each node there is no balance. So whatever comes in is the same as what goes out. Okay, so one attempt for this was to do something of this form where you look at a path. Okay, and if you look at the first path here, this SABHT. So here the smallest capacity was this arc here. This was a limiting one. So then that uh, yeah, you just propagate 3 on all the other links as well. Okay, and then the next one is probably to look at this path. So SCGHJ, and here the limiting one was 2. Okay, so but fortunately even this would support the 3 plus 2, so that was fine. Okay, and so on and so forth. So this was one way you could construct a flow, but you don't know that this is indeed the max you could do. Okay, so in order to find out what was the max, I mean, like, yeah, so the idea was, from this point, you try to improve it further. So here, if you see, there was some backlog in this point. Okay, so at this point there were just two here, two, 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 but actually you could have sent four and split some along this path. So you could send some along this uh, path. So that was what gave the optimal. So if you see here, the optimal solution had four, and then a two, and two, and again a joint here at T. Okay, so now this flow gave a value of 11, but how do you know that that was optimal? So that for that, what we needed was the min cut. So in the sense that you're sending things from S to T, but another way to think of this problem is that if you cut the network in this manner, any manner, if you're able to cut the network, the flow you send cannot be more than what comes out of this cut. Okay, so what comes out of this cut is actually like BH. I mean, if you look at the capacities on these links which come out of this cut, so you have 3 and 2, so that gives 5, and I guess this one was 2. So from here, so this was 2, so 3, 4, 5, 6, 7, 8, 9, this one, and 11 here. Okay, so that was one cut, and the how much ever you send at max, you cannot exceed this value of 11. And this is one particular cut. Now you could find some other cuts too. So let's take this cut, okay, here. So everything that cuts the node T. So you have HT, and this one is not part of the cut because it goes outwards, right? It's not coming into, it's not coming out of the cut. It's coming into the cut, so you don't consider that. So 9, and here you have FT, so that is 6, and here you have IT, so which is 7. So 9 plus 6 plus 7. Okay, so that gives a cut which is greater than 11. So anyway, that is even larger, so you don't consider that. Now, so in that manner, you could inspect the various cuts and see which one is the minimum value. Okay, so now since you already have a flow of 11 here, and you found a matching cut of 11, yeah, it must be that there is nothing lesser than 11. Okay, there's no cut which is lesser than 11. And similarly, there's no flow which is larger than 11. Okay, so these are actually two sides of the same coin in some sense, in terms of the objective values. Okay, so what I want to highlight here is, okay, at this point you don't need to really understand like how you can think of this problem as a cut, or why the cut formulation came up and all that. That will, and we come to it later.
Ma'am,
But the yes.
uh, ma'am, so to find the optimal solution for this flow network, we need to find every possible cut. I mean, that is having some value, and then find maximum like that.
If you're looking at it in terms of cut,
Yes,
first thing you would do is you would find every cut and choose the one which is
which is the least one.
the least one. Because whatever comes out from the flow, whatever flows from S to T, for any cut you make, it cannot increase beyond the value of any cut. Okay. So then the idea is what is the lowest possible value of the cut? Because every flow value
Okay.
you send will be less than the value of every cut. Right? So if you want to find the maximum value of the flow, you try to find the minimum value of the cut. Okay, so but anyway, I mean, this, it might look a little confusing at this point, but I mean, I'm not gonna expect you to follow how all the logical arguments of how we went about doing this. This will come later, but the idea here is that you need both these parts, the flow as well as the cut, the exact flow constructed as well as the cut value. Okay, in order to say that you have reached the best point, you've reached the the optimal point. Okay, so you cannot do one. I mean, you cannot, if you just construct this flow of 11, you don't know whether you're done yet. Okay, so it's not complete. If you just construct a cut giving you a value of 11, you don't know whether you're done, because how, what if there was a cut of smaller value? So then it could mean that the flow that you sent couldn't exceed even a smaller value. So the idea is like, yeah, you need to look at both these things together. Okay. So anyway, we'll come into more details at a later point when I teach you linear programs. So this is just to give a flavor. So actually both these problems, the flow as well as the cut problems, these both are different optimization problems themselves. Okay. But they're related in some sense. Okay. So yeah, this it's a concept called duality, which we will see later. Okay. So now yeah. So moving on, so then we looked at this safe IIT campus and where we constructed, like which are the nodes or which are the points at which you need to position guards so that you have a safe campus. Okay, so that all roads are visible basically. So then we constructed a configuration where there were six guards that you had to position. Now, in order to find whether six was indeed the best, it was not clear. Okay, whether can you do something better than six? So in this case, it turns out one way is you can possibly enumerate all the solutions. Okay, so six was the best here. It's I mean you have to take it because I'm just telling you that six is the best. It's a known result. But the way you do that is you enumerate all possible sets. Okay, so the number of subsets of the vertices here, so that is 2 power v, right? If v is the number of vertices, so in this case there are 10 points. Okay, so A, B, C, D, E, and I mean all these points. There are 10 of them, and out of these you want to look at all the subsets. Okay, so this value is 2 power 10 if you remember. So are people okay with this number? Is 2 power 10? Any questions on this? All of you are comfortable? Yes, no. I know it's morning and it's probably have just woken
Yes,
up.
ma'am.
I've just woken up, so okay, good. So okay, so the only way you could verify this is in general, it's to look at all these 2 power v subsets, okay, and see which one is the smallest and which one is a valid configuration. Okay. By valid configuration, it means that all roads are visible. If you select these vertices, you want every edge in this graph to be covered by at least one vertex. So this is actually, you might have seen this. This is called the vertex cover problem. And this is known to be hard, okay, in general. So now if you want to do this for a large network, so this was a kind of small network with just 10 nodes. So maybe 2 power 10, you can do it on a system. You can just code it up and actually go over all the choices. But if you wanted to do this for this kind of a real town, okay, so where this is a snippet of Bangalore, and if you look at all the roads here and you construct this kind of a network, it's possibly going to be, it's going to have a lot of intersection points, okay, a lot of vertices and stuff. So then enumerating all the choices, that's not even feasible. Okay, so here, so this is to sort of give you a flavor of these easy and hard problems. Okay, so the first problem that you saw about sending oil from one point to the other, that's the max flow problem. And turns out that has a polynomial time solution. Okay, you can solve it easily. But this other thing about constructing a safe network, the vertex cover problem, so that is NP hard, and it's unlikely that you can solve it in polynomial time. Okay, so the idea is some problems are easy, some problems are hard, and if the problem you can show that it's an easy problem, by easy, you should take it as it just means the polynomial time solvable problem. So if it's the case, then you find efficient ways to solve it. But if not, then you there's no point in trying to find an exact solution there. So you try to find some approximations that do well. Okay, Now, even for this particular case that you saw, we could construct the the cover easily. To some extent, it was easy. So actually, it turns out that this instance that I showed you was one of the easy instances. Now, what do we mean by that? Like when the problem is hard, the vertex cover problem is hard, but that doesn't mean that it's hard on every particular example you take. For every road network, it's not a hard problem. So this is an easy example of a road network, and for this case, you can do it in polynomial time. But in the most general, if you give me any arbitrary road network, that may not be the case. So that's what we mean by it's hard. So there are some particular instances of the problem which are hard. Okay, but it doesn't prevent some easy instances from being there. So one thing that people do is you also try to find some special polynomial time solvable cases. Okay, so that's been the kind of flavor of things that you want to do in this line. Okay, so now I just want to, like spend some time on modeling these problems. You saw two problems. Okay, so let's just try to see how you can model this as a math program. So a mathematical program is also an optimization problem. So let's start with this flow, okay, this problem. You want to send some oil from S to T and you want to, do this thing of maximizing the amount in this network. And how can you formulate this? Okay, so, let me just open this in Ocular maybe. Okay, so yeah. Okay, so it's the flow problem, and again, you want to send something from S to T, and you have some capacity. So let me call the capacities as Cij, capacities of the links. So, for arc Ij, it is Cij for every Ij in the network. So the set of edges. Okay. Um, Now, what do I want to do? So if you remember the constraints that you have, let's try to write them first. So I will say that, I'm also going to associate each link with a variable xij. So this is the flow that is being sent from I to j. Okay. So yeah. So now, can you tell me like what were the constraints that you had? Like the problem had some things, right? That you want to be well within the capacities, and you don't want any, anything to be balanced out at each of the nodes. So can you can you tell me some of those things? Like, can you express it in terms of these x's and c's? Is a problem clear to you all? Like what we're trying to do?
Yes, yes, ma'am.
Okay, so one
Can you
of
switch
you,
back to the screen?
yeah, sure. Yeah, so I want some of you to
Summation
try.
xij, that is all the flow to j, is equal to summation j k says summation over k.
So summation xij.
This is summation over I is equal to summation xjk, where summation over k.
So what is the summation over? Like, so this is I is, what is this I?
I is basically all the links that are connected to the node j.
Okay, so all the nodes which are connected to J, right? So
Yes,
such that I, J in E, and so this is all the nodes K such that JK is in E, right? So this is true for every, so for every j, right?
Then Xij is less than equal to Cij and more than or equal to 0.
Okay, xij is less than cij and xij is greater than 0. So who answered this?
And this is Rohit S. I
Rohit.
said
Okay.
both.
Okay. So I would like, I mean, since I'm on this screen, I would like you guys to, when you interact, just tell me your name also so that I know who I'm talking to.
Yes, ma'am.
Okay. Okay. So, yeah. So is this clear to you all? So, what these constraints are? Are there any questions on this? What these are representing?
Yes, ma'am. It is inflow is equals to outflow on any
It's
given vertex I.
right. And also, you have the capacities as an upper bound, right? So,
Yes, ma'am.
okay. So who was this now?
Ma'am, this is Tushar Lone.
Tushar. Okay. So, yeah. So, yeah. If you guys are not clear, if somebody is unclear about this, please let me know. Okay. Okay. So, yeah. So now these are the constraints of the problem, and you wanted to maximize something. Okay. You want to maximize the flow that's going out from node S. So, can you tell me how you would capture that? Somebody? Anybody wants to go ahead? Okay. Are you all there?
Yes,
Excuse me,
ma'am.
ma'am.
Okay. Yes.
Ma'am,
So, yes.
I had a doubt. For the first set from summation of xij, should it be less than equal to summation of xjk?
No, this should be equal to for every node because you don't want any balance, right? So here, if you see, oops, I don't have it here. So just give me a second. Yeah. So you remember at every node. So for at A, for instance, you want everything that's coming in to exactly match something going out. Okay, there's nothing that you can store at each of these nodes. So if you put that it's less than or equal to, um, sorry. So if you say that xij, just give me a second. It's for some reason. Huh. So if you say that, instead of equality, this is less than or equal to, what it would mean is that, you're sending in something less than what is going out. Okay. So you want things to be exactly matched there. Okay. So otherwise you will have something, it would be something of this form. So wherein you send maybe one here, but four outside. Okay, so one unit has come here and four units have gone out. So that is not, that's not a meaningful solution, right? So that's why you want this to be exactly equal. Okay, and this should be true for every uh, vertex other than S and T. Okay, so is your question answered?
Yes, ma'am. Thank you, ma'am.
Okay, all right. So, um, yeah, so any more questions about these constraints? Okay. So if not, then let's try to see what we wanted to maximize. So the thing that we wanted to maximize is you had things coming out from source, a lot of things, right? And you had the terminal node and you had things coming in. And in between, there was some flow that was going all about. So the thing you wanted to maximize is the flow going out from S or the flow going into T. So either ways that was fine. So you want to max
Summation over J x S J.
XSJ, okay, summation over J, yeah, such that all is j's are in E, the sum of all the edges, right? So this is what you want to maximize. Now, there's also going to be one other constraint, okay, which typically you put. So that idea is like, whatever comes out from here is exactly same as what comes in. Okay, so that's another way of modeling it. This is usually, it should be sufficient, but uh, usually the flow balance, like in order to make it a little more compact, what they write is something of this sort. So x I j. So this is the same, all I j in E. So minus x uh, j k for all k such that j k is in E. So this is equal to 0 for everything other than S and T, for every j not in ST, and it's equal to some element, say V, for j equals S, and minus V for j equals T. And then you try to maximize this V, okay, and subject to also capacity constraints. It's basically the same as this. It's just that you are, capturing um, the whatever is outgoing minus incoming through this at the nodes S and T using this variable V. Okay, and then you're trying to maximize V. Okay, so this is actually what is called the linear program. It's a mathematical formulation to do the to write the to solve this problem. Okay. Now, some of you may have seen some other algorithms for the same problem. So that is approaching it in an algorithmic manner. Now, in this class, what we are going to do is we are trying to see how to formulate the problems in this manner. And so now you have a general framework and you're going to analyze how to solve problems of this kind. Okay. So let's just, so is this clear to you guys, this formulation, how we wrote it? We're just trying to capture whatever constraints we have and whatever we want to maximize or minimize, we're just writing it in a compact form. Okay.
Yes, ma'am.
So, okay. So now let's also take the other example for this one of the security guards. You have to position them at the campus. So let's just try to do this also. Let's try to write a formulation.
So, ma'am, that other screen, could you go back?
Yes.
Shouldn't that be uh, plus V if J is equal to T and minus V if J is equal to S? Small
Oh, you
correction.
see this is flipped, minus b and b.
I think so.
Okay, possibly. So x I j. So here j is everything incoming, and this is everything outgoing, right?
Yes, so outgoing
So
is negative.
yeah,
If J is the source, then negative should be.
right. This is true. You're right. Okay. So thanks for pointing this out. Yeah.
Yes, ma'am.
Okay. So yeah. So if this is all right, let's get into the other problem. Okay. So maybe let me open another. Okay. So let's just try to write what happens for this problem where you need to position guards at each of the points and every road should be visible. So if you position a guy at this point, then all the roads are going to be visible. So you want to ensure that all roads are visible. Okay. So, and you want to minimize the number of guards you need. Okay. So can you tell me, anybody wants to attempt? So first, like we did, like, can you tell me how to encode these constraints? So let me just make the start easier. So let us say xi is a variable which says that it says I if a guard has to be positioned, guard must be positioned at vertex I. Okay, so this is the variable. xi. So you have this for every I in the every vertex. So can you think of what constraints you need here? So remember the thing was that any road you take, one of the two endpoints, okay, that must be covered. That there must be some security at one of those endpoints. So any thoughts how you could capture this? Can someone try?
I know we have to minimize the summation of xi's, but the constraints, not entirely sure how to write those.
Okay, so you're saying it's minimize summation excess. So who was this?
Again, Rohit.
Rohit. Okay. So this was minimize the summation of excess. That is right. So yeah. So the constraint was what? Let's just think of it again. Any edge you take. Okay. So you have ij. So at least at one of the endpoints there must be a guard. Okay. So yeah. So does anybody want to try, or I can tell you, but I just want to give you guys a chance if somebody wants to attempt.
For
Ma'am,
all edges
Uh, can you say again?
I'm Rohit here again. For all edges ij, there should be either
Okay.
xi or xj. I'm just guessing, not entirely sure.
Okay. Okay. For all ij's,
Either xi or xj must be present.
either xi or xj must be present. So yeah, that's essentially the idea you want to capture. But how would you write that in terms of math? So let me give you one more hint. So let me say all the xi's, you're going to constrain them to be 0 or 1.
we can say that uh, xi plus xj for all I comma j must be greater than
Mhm.
0.
Must be greater than 0. Okay, so who is this?
It's Ankit. For all ij,
Ankit.
that belongs to image.
Okay, this is what you mean, right? Xi plus xj is greater than equal to 0.
Yes, ma'am.
Greater than, not greater than equal.
Greater than 0.
Greater than, not equal
Oh,
to.
greater than. Okay, okay. Good, good, good. Greater than 0. Yeah. Yeah, this is actually exactly what it is. So if you put greater than equal to 0, then you would just put all xi's as 0. So that would be the optimal. So yeah, this is true, or you could also say xi plus xj greater than equal to 1. It's the same thing. So okay, so is this clear to you all how this has come?
Yes, ma'am.
Yeah, right. Okay, so you take every edge, and at least one of them should be having a value of xi equals to 1, and so that's what this is. So this is one way. So this is what is called an integer program, or this okay, integer programs generally you can have xis as 0 1 to any of the integers, and this is a specific case where you have a binary valued variables. So this is a binary integer program. Now actually another way you could write this, so this is one formulation. Now another way is you keep the same thing, minimize sum of xi, same thing, xi plus xj is greater than 0 for all ij. Okay, and instead of the 0 1 constraint, another way is you could write it as xi times xi minus 1 is equal to 0. Okay, so you can see that these two are capturing the same information. So the feasible points here is either xi is 0 or xi is 1. Okay, so it's just that the form is slightly different. So here, if you write it in this way, you have a quadratic constraint. Okay, but here you have everything is linear. So these are like different classes of problems, and they have been studied differently. So the theory which looks at integer programs does things in a different way, and theory which looks at quadratic programs does things in a different way. Okay, so what I want to say here is that there are different ways to formulate a problem. Now, it's not that every way is going to, give you the same. I mean, yeah, everything gives you the same solution, but in terms of the solving powers, the things will be different, right? So that you have to be a little bit careful. So that's one thing. So maybe I'll just give you another example to bring out this point. Okay, so one more thing before I move on here is, this xi plus xj greater than 0. Usually, I mean, this is actually correct. There's nothing wrong about it. But usually, these kind of strict constraints are hard to capture in an optimization solver. Okay, there are some technical issues there, and for that, people usually prefer to write sorry, this kind of, greater than or equal to. Okay, so that's one thing you could keep in mind. So in other ways, you can try these things out in a standard solver like Gurobi or Python. So there you would see that, it throws some issues when you try to, enforce these kind of constraints. Okay, but in theory, it's fine. There's really no problem with it. Okay. So now let me just try to tell you another case. Sorry. Okay. So now the thing is, okay. So you can provide these formulations for any problem, but you should be careful about when you want to use optimization, when you don't want to. For instance, like if I want to just take a sum of you know some, I'm given some numbers C1 to Cn, and suppose all of them are greater than 0. I'm given these things, so these are given, and I just want to add these numbers. Okay, so everyone knows how to add numbers, so you'll just compute the sum. Now even this you can write as an optimization problem, really. Okay, so one thing, like how we did earlier, is just keep some variable like this, ci xi and xi in 0 1. Okay, so this is actually a perfectly fine, right? I mean, it's an optimization problem and it's going to give you the sum. But do you really need something like this? Okay, where you know how to add numbers. You don't need to get into the tool of optimization for this. Okay, so if you look at this example, another way is, okay, so this is an integer program. Now you can also write it as a linear program. So you can write something like this: minimize t, and t is greater than, so we can call it minimize x. Okay, so x is the variable and x is greater than sum of ci. Okay, so this is also a perfectly valid formulation, right? I mean, you have the sums, you want to find the smallest number which is greater than summation ci. So yeah, so this is a linear program, this is an IP. So you can do all sorts of things, but you have to use your discretion to decide whether really you need to go into the tool of optimization. It's a powerful tool because you can capture rigorously in all these formulations. But yeah, uh, just a word of caution. Okay. So. Uh, Okay, so that was about modeling. So, sometime, when I give you the first assignment, I'll also give you some exercises to model. I mean, it's a very important part of optimization, like how to model problems and stuff. So, so let me just continue from this point. So you saw these mathematical programs, some two examples you've seen. So in general, the form is something of this form. So you have a minimize or maximize, but okay, so it's something like you want to optimize. And here there's a min, and there's a function f of x that you want to, optimize. Okay, so f is a function and x is the decision variables. For instance, for vertex cover, we saw like the xi stood for, whether you want to position a guard there or not. And for the other case, for the flow problem, you had xij's corresponding to each of the arcs. Okay, so x is a decision variable and there's a constraint set. So you want to minimize some function subject to x lying in some constraints. So x in some constraint set. So whatever we did so far, like whether it was a flow or whether it was a vertex cover, we were trying to capture this omega using some inequalities or equalities. Okay, so that's the general form of an optimization problem. And for our purposes for this course, omega is going to be a subset of Rn. Okay, strict subset of Rn. Now there are optimization problems where you can go outside the real number space and stuff, but for this course we won't do that. And the function to be optimized in here is going to be a single objective. So f is Rn to R. Okay. Now there is a stream which looks at multiple objectives where the function, there are multiple functions you want to optimize. So you write that as a function from Rn to some, say, Rm. Okay, so it's a vector of functions you want to optimize. But here, for this case, we are only going to look at the single objective case. And in terms of notation, we would write x star as argmin of f of x to say that x star is the minimizer of f of x. Okay, so now in the classification of these optimization problems, there are different ways. Okay, so based on the objective function, the feasible set, and the decision variables. So so I've just broadly listed these kind of classes. So unconstrained optimization is where you don't have any particular constraints in the sense that it's the omega that you're taking is all of Rn. So like in the earlier cases, we wrote some constraints, right? That is not going to be there. It's just all of Rn. Now, in the case of constrained optimization, you're going to have omega as a strict subset of Rn. So this was a case that we saw, right? And we had some inequalities and we had some equality constraints. Okay. So these two usually have different techniques. So we will cover these in this class. Okay. So unconstrained and constrained optimization problems. Now, this is one classification. Now, another way is based on the functions that arise in the objective or constraints. So, based on these functions or even the objective. So, linear programming is where all the functions that arise are linear in the decision variables. So, x is the decision variable here. And so, if you see the objective is linear in x, and here too, the constraints, so this is a matrix kind of constraint. So Ax equals B. So here you have like several equations in X. Okay, so these equations are all linear. So that's what a linear programming form is. Okay, now a quadratic programming form is where at least one of the functions is quadratic. Okay, so what we saw, like the match flow example, that was a linear program. Okay. Now, based on the domain of decision variables, so we saw cases where things were 0, 1, and we also saw a case where the linear program it was continuous. So based on that, there's a classification. So this is another stream. The integer programming is a quite well studied stream. It's also called discrete optimization or even combinatorial optimization. So here, one or more of the variables are restricted to be integers. So there is some hardness associated with these kind of problems, and we won't be going into these techniques for this course. Okay, so that's a different course by itself. Okay. Now, other types of optimization problems are semi-definite programming, second order cone programming. So you don't have to know these at the moment, but these are like dependent on the x's, right? The domain of these variables. So in the case of semi-definite programs, these x's themselves are matrices, okay, and they have some particular constraints there. And second order cone programming is a specific form of what is called cone programming. These x's lie in what are called cones. Okay, so this is just to tell you that it's a huge field, it's a vast field, and there are different classifications. So here we are just going to look at unconstrained and constrained optimization problems, and we would cover some part of LPs also. So it's not that these classes are like, if it is in one, it's not in the other. For example, a linear program is a constrained optimization problem. Okay, and even integer programming is a constrained optimization problem, but with integer constraints. Okay, so what we are going to look at is a general technique for unconstrained and constrained optimization. So now, we got a feel of hardness of problems. So is any particular class easier than the other? So if you look at discrete and continuous optimization problems, so continuous optimization, like all the variables are, lie in some band. So for example, xij less than cij, between 0 and cij. That was one example we had. And if you see the kind of, the feasible set, that is an infinite set. Okay, so it's actually uncountable. Okay, and whereas if you take discrete optimization or even the vertex cover problem, uh, if you remember, like, you had to enumerate all 2 power v combinations. Okay, so 2 power v is exponential, but it's still finite, right? So it's countable. So in that sense, is discrete optimization easier? So one might think that that is the case, but really that's not. Okay, so are you guys familiar with countable and uncountable sets?
Yes, ma'am.
Okay, so anybody who is not familiar with it? Okay, so are there any answers here? Okay, sorry, I didn't see these at all. Like I think you should speak up if you want to answer. Okay, so I guess all of you are familiar with countable and uncountable sets. So in discrete optimization, the feasible set, the all possible alternatives you have is countable. That set is countable. So you can just enumerate them. So does it make the problem easier? And the answer is no. So um, yeah. So okay, so this is what I wanted to show you was a set of easy and hard instances in both these problems. Okay, so discrete, whether it's discrete or continuous, there are easy problems as well as hard problems. So for example, in discrete optimization, the hard problem was vertex cover, and you probably are familiar with the knapsack problem. So these are hard instances. But there are some easy instances also, which is linear assignment and network flow. So we'll cover some of these in the later part. And in the continuous optimization class, so linear programs are polynomial solvable instances, and similarly, the second order cone program is a easy instance. But a hard instance is what is called the polynomial optimization problem. So in general, if you look at both these, both are hard. Okay, discrete as well as continuous optimization problems have hard instances. Okay, but some classes of problems in continuous optimization, they have some efficient algorithms and guarantees. So because of the continuity, it helps in some way. And that is what we'll focus on in this course. Okay. Now, another thing I want to say is about convex optimization. So there's a lot of this thing about if the problem is convex, it's easy. Okay, so we will cover some aspects of convex optimization too in this course. So it's traditionally believed to be easy, but really that's not the case. So there are here too, there are easy and hard instances. So why is convex optimization special? So the reason is because there are some desirable properties and some efficient methods for some classes. So for example, for linear programs, there are some efficient methods. For semi-definite programming, there are some efficient methods. Okay, and also for some discrete optimization problems, you could use convexity to get to some extent to solve the problems. So that's why convex optimization, there is a buzz about it. Okay, so yeah, so this is just to give you an overall feel of this field. And so just before I wind up this class, some thoughts of research that's been going on in optimization. So there are several journals, okay, that people uh, publish their advances in, and it's still a growing field. So these are some of the good venues if if you're interested to pursue research, like if you want to do a PhD or further masters. So these are some of the venues you would look into, and so some of them are very theoretical, like MathProg, CM Journal, and OR, Math of OR. They look at the applied side. I mean, of getting formulations, even sometimes writing some formulations for some real problems. It's not easy. Okay, so these focus on some of those aspects, and there are many application-focused journals as well. And in computer science, like we have NeurIPS as one of the papers which you can find some optimization work too. Now, for several people post their work in progress papers in these sites, Optimization Online and Archive. So, okay, so these are some of the venues you could look at if you want to know of the advances. So this class covers the introduction to optimization. So from the next time on, we'll be looking at some of the preliminaries in terms of linear algebra and calculus. Okay, so I think I'll stop here. And yeah, if there are any questions, we can chat. Otherwise, you can move on. So thanks everyone. You
Ma'am,
go ahead.
a small
Yes.
request.
Yes.
Can you
Tell me.
post the Google Meet link in the classroom description box? I'm not entirely sure how it works, but the Google Meet link in the classroom description box. Like
Okay.
there's a place for the video connection or something.
Yeah, yeah. So I think that had a default link that got generated. That's the one we were using.
Oh, okay.
Let me try to see if there's something I can do on this.
Otherwise, no problem. It was like a very small request that I had.
Sure, sure. Yeah. Anything else? So actually, I'm done. So you're free to leave the class.
Okay. Thank you, ma'am.
Thank you, ma'am.